Today. So for today's presentation, we'll be introduced autonomous tag project sponsored by MP Ming Fang. So we'll be introduced journey for this whole project and also our collaboration work with EBB and the TCOMs on the technology development and Chua. So for today's presentation, we have three parts. The first part, our partner, Dr. Liza from ABB, will introduce the key architecture and also the collision detection, collision avoidance algorithm. Then I will be cover the digital twin development, which has been carried out by our technology collaborator TCOMs. And also finally is the journey for our project Minowa, which is the Capital Autonomous Tag project. We will be introduce the whole Chua and also our effort to get the first in the world autonomous notation from ABS. So before we start the presentation, I have to, other than the three presenter here, I also want to give the special thanks to our collaborator, especially MP is the main sponsor for the whole project. We have been received a main fund for the project, which is in line with MP's MASS initiatives. We also have to give special thanks to Capital Smith Toys, which is not only provide a tag for the retrofit and the Chua, they also provide quite valuable input from the operation set, which I think is a unique domain knowledge for autonomous technology. And also have to thank ABS, the American Bureau of Shipping, which have been provide a lot of input in our journey to obtain the first in the world autonomous notations, and also when we develop the CONOPS document. Also, M1 is our connectivity providers, which support our remote control operations. So the whole project started from 2019 as part of an initiative from MP on the marine surface vessel development. So for the whole project, actually, we have different phases. So we have been using a conventional manual tag provided by Capital Smith to retrofit with advanced remote control and autonomous sensors and software to make it a remote control and autonomous capabilities. Then we have been conduct the first remote control demonstration and the trial last year. After the first phase, first remote control demonstration, we have been going through 6 months of data collections in Singapore port water with all the newly installed sensors, like camera, radar, LiDAR, and the wind sensor, and all the sensors we can gather the data. So with all this data, we have been trying to train the autonomous software and use for the image recognition, object identification, and also using the traffic data we have been collected to design the appropriate test plan and the trial plan for the autonomous Chua. So finally, we have been complete the autonomous upgrade and Chua starting from December last year. Actually, we just finished the last autonomous trial last week. Now I pass over to Dr. Liza. He will be introducing the architecture for the...
Thanks, Dr. Chen. So I'm Liza from ABB. I will describe on how ABB autonomous control system works. So just like humans, in any situations, we use our sensors such as our eyes and our ears to receive information of the environment, send this information to our brain, and process the information, and if necessary, our brain will give the signal to our arms and legs to take the action. So we apply this similar concept over to our autonomous control system. So here we have ABB Ability Marine Pilot Vision System, which acts as our eyes to sense and perceive the environment. It receives and sees the environment using different sensor sources like the solar equipment, the cameras, and other sensors on board. And then we have this autonomous control, autonomous collision avoidance module as part of the pilot vision system that acts as our brain. So in this brain, we receive the different information from the data inputs, fuse them together, as well as uses artificial intelligence for the visual perception. And then we will analyze this data inside this module and determine whether an action is necessary. For example, if a collision risk is detected, then our system will then plan an avoidance path to avoid this collision scenario. Then this collision path will then send to this, our ABB pilot control system, which will take action and then drive the vessel along the new path to avoid the collision. So in this project-wise, ABB delivered this end-to-end integrated solution for both the autonomous and remote control. It comprises of the pilot vision system that I mentioned earlier for the situation awareness and intelligent perception, the remote control, the autonomous control avoidance system, as well as the pilot control system for this advanced maneuvering and control of the vessel. So here we can see a conceptual illustration of how the system is set up. Firstly, we look at the autonomous system on board, where we have in the yellow box, there's different common sensors on board, such as the wind sensor, gyro compass, radars, AIS. They act as a data input to our system on board. In addition, we also have camera for the visual perception. And on the operator station on board, we also have a user interface where the operators can control our system from there. As Dr. Chen mentioned, this is a retrofit project, so we actually have a physical switch that you can see in the blue box below to switch between the ship's original conventional control and our ABB autonomous control. So of course, there are logic that have been implemented such that we only switch over when certain safety conditions are met. So this autonomous system on board is fully independent from the connectivity system. So for the onboard system-wise, it is an end-to-end this closed-loop control from the machine perception to the control itself. So then for the remote control part, this is where the connectivity system comes in. This remote control portion involves setting up an operator station and an onshore, and data transfer between onboard and onshore. This remote control station onshore is exactly very similar to what we have on board. The only difference is that there is a digital view that has to be implemented for the onshore operators to know what is happening at the surrounding of the vessel. And this is done by streaming this camera live stream over from onboard to onshore. So this is an overview of how the system is set up in the vessel. And then next, I will go into this, the process of the autonomous collision avoidance. So the very first thing is to be able to track and detect the targets. So we do this by firstly having a using machine learning to develop these computer vision models that enable us to detect the targets. As we can see something like this. And then this information is passed to the sensor fusion portion along with other data inputs such as from radar and AIS. We combine the information together, and this allows us to be able to detect the targets and to track the vessel's movement. So being able to track the other targets, other vessel movement, and also knowing our own speed, our own vessel speed and direction, heading, we will be able to predict whether or not there is a collision risk involved based on the distance to the closest point of approach and the time it takes to reach there. So then there are also other information available in the system that you can see here from the user interface, such as other target vessel speed, course over ground, as well as their range to our own vessel. So, so we go to a case here where a risk has been detected. So let's say if in this case, our own vessel that you see here is traveling on a planned path. If let's say there is a vessel that comes in our way, like in this case, a head-on situation, and then our system detected that this is a collision risk because it has a closest point of approach under a certain meter in a certain time, then our system will start to plan for this avoidance action. So internally, our system determines what is the avoidance action that is necessary. Once the avoidance action suitable solution is found, then we can see that in this next slide that avoidance route is planned along to avoid this collision risk. Internally in our system, it is continuously calculating and assessing the situation to see whether we need to replan this path. If, let's say, for example, this vessel heading on to us changes its direction or speed, and this collision avoidance path that has been planned is no longer safe, a new path will be planned. And also, yes, so now we see here that this collision path is now activated. And then This information will be sent to our pilot control system, which will navigate the vessel along this collision path, collision avoidance path that has been generated. So just to show another view that we can see here, the augmented reality view from our user interface, we can see the target vessel there and our vessel traveling along the collision avoidance path to avoid the vessel. So now I'll pass on to Dr. Chen to continue the rest. Thank you.
Yeah, so for this digital twin is our collaboration work with TCOMs, because we think one of the unique challenges for autonomous shipping is the accurate prediction of the trajectory of the vessel, especially when it's the effect of wave, wind, and current, the environmental loading. So we have been developed this framework with Technology Center for Offshore Singapore, TCOMs. We have using this, not to go through the details, I think a little out of timing. So we also did a model test in TCOM's basin. We do all the pre-sea trial simulation to see how the environmental loading has been affect the trajectory prediction of the vessels, and also have been provided input from the simulation and the sea test, and also the model test to ABB to feedback and further tuning the system. So here is some result have been doing simulation we have been doing in TCOMs. We have this to try to see how the current and wave is affect the control of the vessels, and how is the deviation from the planned waypoint and the actual execute route. Okay, so we come to the instructions, the whole journey of the project. So from late 2020s, we have been using this conventional autonomous tug from KRC. We have been installed quite a lot of autonomous sensors and sensors for autonomous upgrading and the remote control, including the X-band radar, W-band radar, LiDAR, cameras, new wind sensors, and also other MU and other sensors, which is not including here. We also convert a two-man cabin room in the bridge in the ship to a central control room of the autonomous system. So we put all the computers, the interface box, and also like the data collection system all in this control room. Then we also do the upgrading to the bridge. So in the bridge, they have a new touch screen for the autonomous control and also a new display for the sensor information. So we also have been setting up a remote control center in Marine Innovation Lab provided by MPA in PS Vista. So here, this is left side is our initial concept. Then on the right side, you can see this is the actual final version of the remote short command center. We have been fully functional. So for this remote control center, the licensed tug master can do the complex maneuvering using the joystick, both joystick and the lever from the short command centers, not just sending the waypoint. So he can really do the manual operation remote control here. We also have been collaborating with ABS to develop the detailed concept operations, to including the intended operation scenario, the operation mode, the field to safe system, and also like the cyber securities, and also test trial, and also the condition for autonomous operations. So all this has been including our CONOPS. So as for the test plan, we also has been discussed with KST, and also based on our collected traffic data from Singapore port to design the most appropriate test route which can comply with class requirement and also comply with the core risks. So during the data collection phase, we have been collecting more than 3,000 hours of data, including videos, radar, LiDAR, and also the sensor like engine data. We have been keep processing all this data to further. We'll be keep using all this data and to do further development in next phase beyond the project. So here you see this is a trial we have been conduct last April. This is the first remote control test has been done in Marina Bay. Actually, you can see this area from MBS. So this is a fully remote control with the captain. To control from short command center in ML. He do the single static and dynamic object avoidance, and also doing the turning circle test. The full video you can watch from YouTube channel. You can just search Keppel and autonomous tug. You can get the full video. I think one of the unique feature we here is in the remote control center we have both lever and joystick. So this is autonomous sea trial we have been conduct. We have just finished last week. So for this autonomous sea truck, we have been designed very complex test plan. We have one dynamic object in both head-on overtaking and crossing from both starboard set and port set. And also not just the constant speed and heading, we have the dynamic object with varying speed and heading as well. We also have been conduct the CDC test with two dynamic objects, which is a combination of heading, head-on, overtaking, and crossing from different directions. And also the object is moving in various speed and heading. This is to try to simulate the challenging scenario in Singapore port, which is the nearby vessel may not always follow the planned route. It can be moved unintentionally or unplanned not as planned. So we can see here, this is actually the onboard camera show the recognized object, and if there's a risk of a collision, the balloon will pop up, and an alternate route will be suggested. Then the tug will follow the route and to avoid the obstacle. So have been the parameters for this collision avoidance algorithm have been tuned quite a few rounds with input from our operator KST based on their manual operations. So we have been tuning like a safe distance, the minimal distance from the target, and when we start to avoid, and what's the preferred route to avoid the obstacles. We have been taking into the consideration from the actual operators' manual operations. So with all this effort, we have been achieved the first in the world autonomous notation and the remote control notations from ABS. So this is quite a good effort. Okay, I think that's the end for my presentation, for our presentation.
Thank you. Okay, we have a few minutes for questions. We have one online question. So this question is a very impressive development. Can this autonomous ship navigate into and out of port automatically? So-called the last mile challenge for autonomous ships. Into and out of port.
I think this more related like the berthing of the tug. This, because for current phase, we are more focused on waypoint navigations, but the capability is I think will require more sensor to be installed if we're coming to the berthing. I think Liza maybe also can add on this autonomous berthing functions.
Yeah, so for this navigating into the port and out of port, it is definitely more challenging. And then, so this is a continuous development in our system as well to integrate the suitable sensors and also test our system for this. So right now, at this phase, for this project, we didn't test this, but this is definitely in our future development for this part of the auto docking functions and navigating in and out of the port.
Okay, thank you. I guess I have a question about the CDCA. So the example that you showed, all the ships are following a straight line. And we know that in Singapore Straits, for example, the shipping lanes follow a curved path or a changing heading. And so how can the system account for this sort of known complexity at first step?
Yes, definitely. For this test case-wise, it is a straight path because of the constraint of the test area that is given to us. But our system-wise can handle a curvature also. We also did a turning circle test with this autonomous system to see how well it follows a curvature.
Okay. Edmund, do you have a question? Can we have this one first?
Yeah, Edmund Brekke from NTNU in Norway. It was very interesting to see all you have done. And you have a lot of sensors involved. And what I'm just a bit curious about is how fundamental is the role of machine learning in this system? Because some of the sensors like radar and AIS, you don't really need machine learning to treat output of those sensors, but you can use it, of course, if you want to. So with this, I mean, let's say the machine learning doesn't work for whatever reason, unpredictable. Would this system still work and be able to detect other ships and avoid them?
Yes, so there is two parts here. For the machine learning portion, mainly we are applicating it to this camera stream for it to have this computer vision model to detect and track the objects and recognize the different types of objects around the sea. So this input is given into another module which fuses the sensor information together. So you are right to say that this AIS and radar information, they do not really need this machine learning portion. So we actually take those information and then fuse it with the outputs from our computer vision model to have the overall sensing on this detection and tracking of the objects.
Okay, thank you very much.
Okay. And then,
Hi, thank you for the presentation, really insightful. My question was it a consideration that when the tug is changing navigation or changing waypoints or changing paths, that it communicates that thing to the target vessel or to the oncoming vessel? So has that been a consideration as part of your collision avoidance?
Yeah, of course, for the demonstration for the sea trial we have to conduct, there will be continual voice communication between the target and also the autonomous tug. Because this is in a controlled environment for all the testing. But I think for the future, the actual autonomous or remote control operation, I think we need to come up with the communication. I think the key, if it's all full autonomous, I think this will be also quite straightforward. I think the challenging will be the mix of the operation mode. If the man-controlled and autonomous control mode, and we all know the man-controlled may not always follow the rules. So that is a challenge we need to consider maybe in next phase. Actually, beyond this project, we are also consider for the, we will discuss with the MPA the possible testing in real traffic with the actual man-controlled vessel. So maybe we can have more input after our next phase.
Yeah, I think that would be important in the long run. Thank you. Yeah.
okay, I think we should move on. Thank you very much for most interesting presentation.